Welcome to Unit 1 of our mathematics series, focusing on matrices. In this session, we will explore how to find the rank of a matrix using two important methods, echelon form and normal form. This lecture is presented to you by JNTUH Technologies Private Limited. Let's begin our mathematical journey. Question 1. Define rank of a matrix. Today we'll learn what the rank of a matrix means. In simple terms, the rank of a matrix tells us how many rows or columns in that matrix are linearly independent. That is, how many of them carry unique information. Imagine a matrix as a collection of data. If some rows or columns can be written using others, they don't add anything new. So the rank helps us find out how much real information is in the matrix. Mathematically, we write it as rank of A, or rank A. To calculate it, we usually convert the matrix into a special format called row echelon form, and then count the number of rows that are not all zeros. Each of these non-zero rows tells us one dimension of information. Let's look at an example to understand how we find the rank of a matrix. We are given a matrix A with 3 rows and 3 columns. The matrix looks like this. Row 1 is 1, 2, 3, row 2 is 2, 4, 6, and row 3 is 4, 5, 6. To simplify this matrix, we perform row operations. First, we replace row 2 with row 2 minus 2 times row 1. Then, we replace row 3 with row 3 minus 4 times row 1. After performing these operations, the new matrix becomes row 1 is 1, 2, 3, row 2 becomes 0, 0, 0, and row 3 becomes 0, minus 3, minus 6. This helps us move towards finding the rank, which we'll calculate in the next step. Let's continue with the row operations to simplify the matrix further. First, we divide row 3 by minus 3. This gives us a new row 3, 0, 1, 2. Now the matrix looks like this. Row 1 is 1, 2, 3, row 2 is 0, 0, 0, and row 3 is 0, 1, 2. Next, we update row 1 by subtracting 2 times row 3 from it. That changes row 1 to 1, 0, minus 1. The updated matrix now looks like this. Row 1 is 1, 0, minus 1. Row 2 is 0, 0, 0, and row 3 is 0, 1, 2. Now we check how many rows are non-zero. In this case, 2 rows have non-zero entries, so the rank of matrix A is equal to 2. Question 2. Define normal form of a matrix. Now let's understand what the normal form of a matrix means. The normal form is a simplified version of a matrix that helps us easily find its rank. A matrix is said to be in normal form if it looks like this. A block in the top left, that is an identity matrix of order R, followed by zeros everywhere else. In symbol form, it's written as a matrix with I sub R and zeros. Here, I sub R means an identity matrix of size R, and R is the rank of the original matrix. To convert any matrix into this normal form, we use elementary row and column operations. That means we can swap, scale, or add rows and columns as needed. Once in this form, the rank is simply the size of the identity matrix block. The purpose of converting a matrix into normal form is to clearly separate the part of the matrix that has linearly independent rows from the part that is all zeros. This separation helps us easily find the rank of the matrix. Now let's look at an example. We are given a matrix A with 3 rows, 1, 2, 3, 2, 4, 6, and 1, 1, 1. To simplify this matrix, we apply some row operations. First, we replace row 2 with row 2 minus 2 times row 1. Then, we replace row 3 with row 3 minus row 1. After performing these operations, we get a new matrix. Row 1 is 1, 2, 3, row 2 becomes 0, 0, 0, and row 3 becomes 0, minus 1, minus 2. This is a step toward converting the matrix into normal form so we can find the rank easily. Row reduction to normal form. Let's continue simplifying the matrix to get it into normal form. First, we multiply row 3 by minus 1. This changes the signs in that row. Then we update row 1 by subtracting 2 times row 3 from it. After these steps, a matrix becomes row 1 is 1 0 minus 1, row 2 is 0 0 0, and row 3 is 0 1 2. Next, we simply reorder the rows to place the non-zero rows at the top. So the matrix becomes row 1 is 1 0 minus 1, row 2 is 0 1 2, and row 3 is 0 0 0. This is now in normal form. The identity part is of order 2, which means the rank of the matrix is 2. Final representation. So finally, we have reached the normal form of the matrix. It looks like this. The first row is 1 0 star, the second row is 0 1 star, and the third row is all zeros. Here, the symbol star means that the elements in that position can be any number. They are arbitrary. This structure can also be written in a compact form as a block matrix, identity matrix I sub 2 on the left, and arbitrary values on the right, followed by a row of all zeros. From this final form, we can clearly see that the rank of the matrix is 2. Question 3. Find the value of B such that the rank is 2. In this question, we are given a matrix A and asked to find the value of B so that the rank of the matrix becomes 2. The matrix A has 3 rows. The first row is 1 5 4, the second row is 0 3 2, and the third row is B 13 10. Our goal is to simplify this matrix and then check for the value of B that makes only 2 rows linearly independent. In step 1, we apply a row operation on row 3. We replace row 3 with row 3 minus B times row 1. After this operation, row 3 becomes 0, 13 minus 5B, and 10 minus 4B. The other 2 rows remain unchanged. This is the first step toward checking the rank condition. Continue row reduction. Let's continue simplifying the matrix to find the correct value of B. First, we normalize row 2 by dividing it by 3. That means we replace row 2 with 1/3 of itself. After this step, row 2 becomes 0, 1 2 by 3, while the other rows stay the same. Now we use this new row 2 to eliminate the second element in row 3. To do that, we replace row 3 with row 3 minus open bracket 13 minus 5B, close bracket times row 2. This eliminates the second entry in row 3. After calculation, the new row 3 becomes 0 0 10 minus 4B minus 2 by 3 into in bracket 13 minus 5B. This expression will help us determine when the third row becomes 0, so that the rank is exactly 2. Simplify the expression. Now let's simplify the third element of row 3. We have the expression 10 minus 4, B minus 2 by 3 into in bracket 13 minus 5B. To simplify this, we first expand the expression. It becomes 30 minus 12B minus 26 minus 10B whole divided by 3. Solving this, we get 4 minus 2B divided by 3. So the third row becomes 0 0, 4 minus 2B divided by 3. Now for the rank to be exactly 2, the entire third row must be 0. So we set this expression equal to 0. That gives us 4 minus 2, B equals 0. Solving this, we get B equals 2. Therefore, the value of B that makes the rank equal to 2 is 2. Question 4. System of linear equations in matrix form. Let's now understand how a system of linear equations can be written in matrix form. We represent it as A times X equals B. Here, A is the coefficient matrix with m rows and n columns. X is a column vector with n rows and 1 column. It contains the unknown variables. B is another column vector with m rows and 1 column. It contains the constants from the equations. To solve this system and check whether it has a solution or not, we analyze its consistency. For that, we use the concept of matrix rank. By comparing the ranks of the coefficient matrix and the augmented matrix, we can determine whether the system has no solution, one solution, or infinitely many solutions. Condition for consistency system of equations is called consistent if it has at least one solution. The key condition for consistency is that the rank of matrix A must be equal to the rank of the augmented matrix, written as A bar B. The augmented matrix is formed by attaching matrix B to matrix A. Now let's look at the different cases. First, if the rank of A is equal to the rank of A bar B, and both are equal to n, where n is the number of unknowns, then the system has a unique solution. Second, if the rank of A is equal to the rank of A bar B, but both are less than n, then the system has infinitely many solutions. Finally, if the rank of A is not equal to the rank of A bar B, then the system has no solution, it is inconsistent. Example, consistency check. Let's look at an example to check whether a system of equations is consistent. The system is x plus y equals 2 and 2x plus 2y equals 4. From this system, we can form two matrices. Matrix A is the coefficient matrix 1, 1 and 2, 2. Matrix B is the column of constants 2 and 4. To analyze consistency, we create the augmented matrix A bar B, which combines matrix A and B side by side. So the augmented matrix becomes first row 1, 1, 2, second row 2, 2, 4. Next, we'll simplify this matrix to check the rank and determine if the system has a solution. Row reduction and conclusion. Now let's apply a row operation to the augmented matrix. We replace row 2 with row 2 minus 2 times row 1. This gives us a new matrix. The first row is 1, 1, 2, and the second row becomes all zeros, 0, 0, 0. Now let's find the ranks. The rank of matrix A is 1, and the rank of the augmented matrix A bar B is also 1. Since both ranks are equal and less than the number of unknowns, which is 2, this means the system has infinitely many solutions. So the final conclusion is, the system is consistent and has infinitely many solutions. Question 5. State the conditions for consistency, homogeneous system. In this question, we are talking about a special type of system called a homogeneous system. A homogeneous system is written in the form A times x equals 0. Here, A is an m by n coefficient matrix, x is a column vector with n rows, representing the variables, and the right-hand side is a 0 vector. This means all the equations in the system are equal to 0. Homogeneous systems are always consistent because the 0 vector is always a solution, known as the trivial solution. We'll now explore the conditions under which such systems may have more than just the trivial solution. Consistency and solutions. A homogeneous system is always consistent. Why? Because the trivial solution, where all variables are 0, always satisfies the equation. That is, x equals a column vector of all zeros, will always make A times x equal to 0. Now let's look at the types of solutions such a system can have. If the rank of matrix A is equal to n, which is the number of variables, then the system has only one solution, the trivial one. But if the rank of matrix A is less than n, then the system has infinitely many non-trivial solutions. These are solutions where not all variables are 0. Geometric interpretation. Let's now understand the geometric meaning behind the solutions of a homogeneous system. The number of free variables in the system is given by n minus the rank of matrix A. Free variables are those that can take any value, and they represent the number of independent parameters in the general solution. In other words, they tell us how many directions or dimensions the solution can spread out in. This is also called the dimension of the solution space, or the null space. So if there are more free variables, the solution set will lie in a higher dimensional space. Example, homogeneous system. Let's look at an example of a homogeneous system. We are given matrix A as first row 1, 2 minus 1, second row 2, 4 minus 2. And vector x as x sub 1, x sub 2, x sub 3. The system is written as A times x equals 0. To simplify the matrix, we apply a row operation. Replace row 2 with row 2 minus 2 times row 1. This gives us the new matrix, first row 1, 2, minus 1, and second row 0, 0, 0. Now we check the rank. The rank of matrix A is 1, which is less than the number of variables, which is 3. So the system has infinitely many non-trivial solutions, meaning there are many solutions other than just all zeros. Question 6. Define elementary matrix with an example. Let's understand what an elementary matrix is. An elementary matrix is a square matrix that we get by performing just one elementary row operation on an identity matrix. There are three basic types of row operations. First, swapping two rows. Second, multiplying a row by a non-zero number. And third, adding a multiple of one row to another row. When we apply any one of these operations to an identity matrix, the result is called an elementary matrix. These matrices are very useful in simplifying other matrices through row operations. Example 1. Row swap. Let's look at an example of an elementary matrix formed by swapping rows. We start with the identity matrix I, which is a 2 by 2 matrix. First row 1, 0 and second row 0, 1. Now we swap row 1 with row 2. After this operation, we get a new matrix E. First row 0, 1 and second row 1, 0. This new matrix E is called an elementary matrix and it represents the row swap operation. Example 2. Multiply a row. Here's another example of an elementary matrix. We start again with the identity matrix I, which is first row 1, 0 and second row 0, 1. Now we multiply row 1 by 3. After doing this operation, the new matrix E becomes first row 3, 0 and second row 0, 1. This matrix E is an elementary matrix that represents the scalar multiplication of row 1 by 3. Example 3. Add row multiple. Now let's see the third type of elementary matrix, the one formed by adding a multiple of one row to another. We begin with the identity matrix I, which has first row 1, 0 and second row 0, 1. Then we perform a row operation, replace row 2 with row 2 plus 2 times row 1. After this operation, the new matrix E becomes first row 1, 0 and second row 2, 1. This matrix E is an elementary matrix that represents row addition, specifically adding 2 times row 1 to row 2. Usage of elementary matrices. Let's understand how elementary matrices are used. Suppose E is an elementary matrix and A is any compatible matrix. Then, when we multiply E with A, that is E times A, the result is the same as applying the row operation on matrix A that was used to create E. In other words, multiplying E with A gives us matrix A after the corresponding row operation. So, elementary matrices allow us to perform row operations in an algebraic way using matrix multiplication. Question 7. Find the value of K such that the rank of matrix A is 2. In this question, we are given a 3 by 3 matrix A and asked to find the value of K for which the rank of the matrix is 2. The matrix A is first row 1, 2, 3, second row 2, K 7, and third row 3, 6, 10. To solve this, we will apply row operations and also check the determinant of submatrices to find out when the rank is exactly 2. Our goal is to find that particular value of K which makes the matrix lose full rank but still have 2 linearly independent rows. Row reduction step. Let's begin simplifying the matrix using elementary row operations. First, we replace row 2 with row 2 minus 2 times row 1. Then, we replace row 3 with row 3 minus 3 times row 1. After applying these operations, the matrix becomes first row 1, 2, 3, second row 0, K minus 4, 1, and third row 0, 0, 1. Now observe the third row. It is non-zero unless we force a specific condition on the value of K. To make the rank equal to 2, we'll need to make this third row become 0. Check rank via determinant. To make sure that the rank of matrix A is exactly 2, we need to ensure that the determinant of the matrix is 0. So, we calculate the determinant of A using cofactor expansion along the first row. The calculation is as follows. First 1 into in bracket K into 10 minus 7 into 6. Then minus 2 times in bracket 2 into 10 minus 7 into 3. Finally, plus 3 times in bracket 2 into 6 minus 3 into K. Simplifying step by step, we get 10K minus 42 plus 2 plus 36 minus 9K. Putting it all together, the result is K minus 4. Final result, to make the rank exactly 2, we now set the determinant equal to 0. That gives us the equation K minus 4 equals 0. Solving this, we get K equals 4. So the required value of K for the matrix to have rank 2 is 4. This is the final answer. Question 8. Define echelon form of a matrix. Let's now define what is meant by the row echelon form of a matrix, also called RAR-EF. A matrix is in row echelon form if it follows 3 rules. First, all non-zero rows must appear above any rows that are completely zero. Second, in each non-zero row, the first non-zero number, called the leading entry, must be to the right of the leading entry in the row just above it. Third, all the values below each leading entry, also called pivots, must be 0. These conditions help in simplifying matrices and finding their rank. Example: row echelon form. Here's an example of a matrix that is in row echelon form. The matrix has 4 rows. The first row is 1, 2, -1, 3. The second is 0, 1, 4, 2. The third is 0, 0, 1, 5. And the last row is all zeros. Let's understand why this is in row echelon form. First, each leading entry or pivot is to the right of the pivot in the row above it. Second, all the entries below each pivot are 0. And third, the 0 row is placed at the bottom. So all the conditions for row echelon form are satisfied. Note on reduced row echelon form, RREF. Now let's talk about reduced row echelon form, or RREF. This is a more refined version of the row echelon form. For a matrix to be in RREF, it must satisfy 3 conditions. First, it should already be in row echelon form. Second, every pivot, that is, the leading entry in each non-zero row, must be equal to 1. And third, each pivot must be the only non-zero entry in its column. So RREF is stricter than REF and gives us a fully simplified matrix that is very useful for solving systems of equations. Question 9. To find rank of a 4x5 matrix. In this question, we are asked to find the rank of a matrix with size 4x5. That means 4 rows and 5 columns. Remember, the rank of a matrix is the maximum number of linearly independent rows or columns. For any matrix with m rows and n columns, the highest possible rank is the minimum of m and n. So in our case, the maximum rank can be minimum of 4 and 5, which is 4. That means this matrix can have at most 4 linearly independent rows or columns. Given matrix 4x5, we are given a matrix of order 4x5. That means it has 4 rows and 5 columns. To find the maximum possible rank, we take the minimum of 4 and 5, which is 4. So the maximum rank of this matrix is 4. That's our final answer. It's important to note that a matrix with only 4 rows can't have rank 5, because you can't have more than 4 linearly independent rows when there are only 4 rows in total. Question 10. Find the order of the null matrix below I sub k. In this question, we are given that A is an n by n square matrix and its rank is k. The matrix is reduced to its normal form, which looks like a block matrix. The top left block is the identity matrix I sub k, and the bottom right block is a null matrix or a matrix filled with zeros. Structure and interpretation. Let's understand the structure of the normal form of an n by n matrix. The matrix is written in block form. The top left part is the identity matrix I sub k, and the bottom right part is a null matrix filled with zeros. Since the full matrix is of size n by n, and I sub k is of size k by k, the remaining block, the null matrix, must be of size n minus k by n minus k. So, the order of the null matrix is n minus k times n minus k. Question 11. Find the rank by reducing the matrix to normal form. In this question, we are given a 4x4 matrix A. Our goal is to find its rank by reducing it to normal form. The matrix A has 4 rows. In step 1, we aim to make the first element of the first row a leading one. To do that, we divide row 1 by 2. This transforms row 1 into 1 minus 1, 0, 3. This step sets us up to eliminate the corresponding elements in the rest of the column and move toward normal form. Step 2. Eliminate below using R sub 1. Now in step 2, we use row 1 to eliminate the entries below the leading one in the first column. First we replace row 2 with row 2 minus 4 times row 1. This gives us the new row 2, 0, 6, 0, minus 10. Next we replace row 3 with row 3 minus row 1, which results in a row of all zeros, 0, 0, 0, 0. Then we update row 4 by subtracting row 1 from it. That gives us 0 minus 1, 1 minus 1. So the updated matrix becomes first row 1 minus 1, 0, 3, second row 0, 6, 0, minus 10, third row 0, 0, 0, 0, 0, and fourth row 0 minus 1, 1 minus 1. Step 3. Make pivot in R sub 2 equal to 1. In step 3, we normalize row 2 by making the pivot, that is, the leading entry equal to 1. We do this by dividing row 2 by 6. After this operation, row 2 becomes 0, 1, 0 minus 5 by 3. The rest of the rows remain the same. So the updated matrix now looks like this. First row 1 minus 1, 0, 3. Second row 0, 1, 0 minus 5 by 3. Third row 0, 0, 0, 0. And fourth row 0 minus 1, 1 minus 1. Step 4. Eliminate above and below using R sub 2. In step 4, we use row 2 to eliminate the non-zero entries above and below its pivot. First, we update row 1 by adding row 2 to it. This gives us 1, 0, 0, 4 by 3. Then we update row 4 by adding row 2 to it, which gives 0, 0, 1, minus 8 by 3. Now the matrix is fully simplified and in normal form. The final matrix is first row 1, 0, 0, 4 by 3. Second row 0, 1, 0, minus 5 by 3. Third row 0, 0, 0, 0, and fourth row 0, 0, 1, minus 8 by 3. Final step. Matrix rank. Now, the matrix is in its final simplified form. It looks like a block matrix where the top left part is the identity matrix I sub 3, and the rest contains other values or zeros. This means the matrix has 3 leading ones, which tells us the rank. So the rank of matrix A is 3. Question 12a. In this question, we are asked to find the rank of a 4 by 5 matrix A by reducing it to echelon form. The matrix has 4 rows and 5 columns. Our first step is to use row 1 as the pivot row to eliminate the entries below the leading entry. This means we'll apply row operations to rows 2, 3, and 4 to make the first element in each of those rows equal to 0. These steps will help us simplify the matrix and move toward finding its rank. Step 1. Eliminate entries below R sub 1. In step 1, we use row 1 as the pivot row and eliminate the entries below its leading entry. We apply 3 row operations. First, replace row 2 with row 2 plus 2 times row 1. Second, replace row 3 with row 3 plus row 1. And third, replace row 4 with row 4 plus 3 times row 1. After performing these operations, the matrix becomes first row 1, 4, 3 minus 2, 1. Second row 0, 5, 5, 0, 5. Third row 0, 10, 10, 0, 10, and fourth row 0, 15, 15, 0, 15. Step 2 and 3. Normalize and eliminate. In steps 2 and 3, we continue simplifying the matrix. First, we normalize row 2 by dividing it by 5 to make the pivot equal to 1. So row 2 becomes 0, 1, 1, 0, 1. The rest of the matrix stays the same for now. Next, we eliminate the entries below the pivot in column 2. We do this by replacing row 3 with row 3 minus 10 times row 2, and row 4 with row 4 minus 15 times row 2. These operations help us form zeros below the second pivot and move closer to echelon form. Final matrix and rank, part A. After applying all the row operations, we get the final matrix. It has first row 1, 4, 3, minus 2, 1, second row 0, 1, 1, 0, 1, and the last 2 rows are all zeros. Since there are only 2 non-zero rows, the rank of matrix A is 2. So we conclude that the rank of the given matrix is 2. Question 12b. In this part, we are given a matrix B with 4 rows and 5 columns. The matrix has values filled in all positions. To start simplifying, we apply 2 row operations. First, we replace row 2 with row 2 minus 1/2 times row 1. Second, we replace row 4 with row 4 minus 2 times row 1. These operations are used to eliminate values below the first pivot in column 1, so we can move closer to echelon form and eventually find the rank. After applying the initial row operations, we get an updated matrix. The first row remains the same. Row 2 becomes 0, 0, minus 2.5, minus 3.5, 2. Row 3 is unchanged for now, and row 4 becomes 0, 1, minus 2, 5. To make the next steps easier, we now swap row 2 and row 3. This brings a leading one to the second row, which is helpful for further elimination. The matrix now has row 2 as 0, 1, minus 1, 3, 1, and the rest adjusted accordingly. Eliminate and normalize. Next, we eliminate the second entry in row 4 using row 2. We replace row 4 with row 4 minus row 2. This gives us a new row 4. 0, 0, minus 1, minus 5, 4. Then we move to row 3 and normalize it by dividing the entire row by minus 2.5. This makes the leading entry in row 3 equal to 1. The updated row 3 becomes 0, 0, 1, 1.4, minus 0.8. These steps help us move closer to the echelon form, making it easier to identify the rank of the matrix. Final matrix and rank, part B. In the final step, we simplify row 4 by adding row 3 to it. So row 4 becomes 0, 0, 0, minus 3.6, 3.2. Now if we look at the matrix, all 4 rows are non-zero. This means there are 4 linearly independent rows in the matrix. Therefore, the rank of matrix B is 4. Question 13a. In this question, we are given a 4 by 4 matrix A and asked to find its rank by reducing it to normal form. As a first step, we swap row 1 with row 2 to place a leading one at the top left corner. After swapping, the new matrix becomes row 1, 1, minus 1, minus 2, minus 4, row 2, 2, 3, minus 1, minus 1, row 3, 3, 1, 3, minus 2, and row 4, 6, 3, 0, minus 7. This setup helps us begin the elimination process for the remaining rows. Step 2. Eliminate below using R sub 1. In step 2, we use row 1 as the pivot row to eliminate the entries below its leading one. First, we update row 2 by subtracting 2 times row 1. Then, row 3 is updated by subtracting 3 times row 1, and row 4 is updated by subtracting 6 times row 1. After these row operations, the matrix becomes row 1. 1 minus 1 minus 2 minus 4, row 2 0, 5, 3, 7, row 3 0, 4, 9, 10, and row 4 0, 9, 12, 17. Next, we apply column operations, add column 1 to column 2, add 2 times column 1 to column 3, and add 4 times column 1 to column 4. These steps help move the matrix closer to normal form. Column operations and more row reductions. After applying the column operations, the matrix is simplified further. The first row becomes 1, 0, 0, 0, and the rest of the rows are adjusted accordingly. Now we apply one more row operation to eliminate the non-zero values in row 4. We replace row 4 with row 4 minus row 2 minus row 3. This gives us a new row 4, 0, 0, 0, 0. The final matrix now has 3 non-zero rows, which we will use to determine the rank. Final steps to normal form. In the final steps toward normal form, we first update row 2 by subtracting row 3 from it. Then, we normalize row 2 by dividing it by 5, making the leading entry 1. After these operations, row 2 becomes 0, 1, minus 6, minus 3. Next, we eliminate the entry below the pivot in row 3 by replacing row 3 with row 3, minus 4 times row 2. This makes row 3, 0, 0, 33, 22. The final matrix now has 3 non-zero rows and 1 zero row, bringing us close to the normal form. Final answer for A. To finalize the normal form, we apply column operations. First, add 6 times column 2 to column 3, and add 3 times column 2 to column 4. This simplifies the matrix, so that columns 3 and 4 have zeros in the first 2 rows. Next, we normalize column 3 by dividing it by 33, making the pivot equal to 1. Then subtract 22 times column 3 from column 4 to make the entry in column 4, row 3, 0. After these operations, the matrix becomes nearly diagonal, with 3 leading 1s and 1 0 row. Therefore, the rank of matrix A is 3. Question 13b. In this question, we are given a 4 by 4 matrix B. To start simplifying it, we perform 3 row operations. First, we replace row 2 with row 2 minus 4 times row 1. Second, replace row 3 with row 3 minus 3 times row 1. Third, replace row 4 with row 4 minus row 1. These operations aim to eliminate the entries below the leading element in the first column, helping us reduce the matrix toward echelon form to find its rank. Step-by-step row operations. After applying the initial row operations, the matrix becomes: first row 1, 2, minus 1, 3, second row 0, minus 7, 6, minus 11, third row 0, minus 7, 4, minus 7, and fourth row 0, 0, 1, minus 2. Next, we update row 1 by adding row 4 to it. This changes row 1 to 1, 2, 0, 1. The rest of the rows remain the same. These steps simplify the matrix further and help us move toward determining the rank. In the final reduction steps, we perform several row operations. First, replace row 2 with row 2 minus row 3. Next, replace row 3 with row 3 minus 4 times row 4. Then, replace row 2 again with row 2 minus 2 times row 4. After these operations, the matrix becomes row 1, 1, 2, 0, 1, row 2, 0, 0, 0, row 3, 0, minus 7, 0, 1, and row 4, 0, 0, 1, minus 2. Finally, we swap row 2 and row 3 to arrange the matrix better for finding the rank. Final matrix and rank B. In the final step, we first normalize row 2 by dividing it by minus 7. Then, we eliminate the second entry in row 1 by replacing row 1 with row 1 minus 2 times row 2. After these row operations, the matrix becomes: first row 1, 0, 0, 9 by 7, second row 0, 1, 0, minus 1 by 7, third row 0, 0, 1, minus 2, and fourth row 0, 0, 0, 0, 0. Next, we focus on column 4. We multiply column 4 by 7, then update column 4 by subtracting 9 times column 1, adding column 2, and adding 14 times column 3. This simplifies column 4 to zeros in the first 3 rows. The final matrix is diagonal with 3 leading 1s and 1 0 row. Therefore, the rank of matrix B is 3. Thank you for joining this session. If you like the video, kindly like, share, and subscribe.